So far, we have talked about the convergence issue with logistic regression. So this checked. We only focus on binary logistic regression, but its extension to multinomial case, meaning we have more than two outcomes, and it's straightforward. So I will leave this as an additional rating to students. We focus on linear model, but extension to nonlinear model and is trivial. We can just add the quadratic term or cubic term to logistic regression. And I'm going to talk about the last issue is really with retrospective sampling. So what is retrospective sampling? We usually assume our data Xi's are IID samples from some population of interest. But sometimes we may collect our data retrospectively. For example, in a study on cancer, instead of taking a random sample of 100 people from the whole population, because very likely we're going to end up having all the 100 people are non-cancer patients. So no cancer patients in our 100 samples, unless we sample like 5,000 or a million of people. So this kind of sampling scheme is not very efficient. Instead, if we decide to sample 100 patients and going to collect 100 samples, we may just draw 50 samples from the cancer group and 50 from the control group, meaning the ordinary people. So here the training samples are 50 versus 50. Cancer versus non-cancer. But our test sample, meaning what kind of sample we're going to use our model to make prediction, that our test sample will be the ordinary population or the whole population. Now we realize there's some discrepancy between the training and test. For example, we wouldn't expect in the whole population we're going to have 50% of them, 50% of the people are from cancer patients and 50 are non-cancer patients. So that discrepancy of the training and testing actually impose some challenge, because in order for any machine learning algorithm to work, we have to assume our training and test are indeed generated from the same population or from the same random process. So here let's use Z to indicate whether an individual is sampled or not. Then when we are analyzing the retrospective samples, what we are estimating if we are fitting a logistic regression model is the probability of Y equal to 1 given and Z equal to 1, meaning you are sampled and also the feature is X. But what we really want to learn is the probability of Y equal to 1 just given X. There's no Z. So let's assume the probability we really want to learn indeed fall and can be characterized by this logic, by a logistic regression model, meaning this probability is equal to this kind of sigmoid function and involving intercept alpha and coefficients and beta. Here I isolate the intercept and the coefficients associated with non-intercept features. Now the question is, if we really care about the model 2, and we want to estimate those alpha and beta from equation 2, can we learn them from a retrospective sample? It turns out for logistic regression, we can actually learn beta from the retrospective sample, and the only difference is alpha. We're going to have a different intercept, but that can be easily fixed to meaning we can, based on the intercept we learned from retrospective sample, if we just do some small adjustment, and that would be equal to the real alpha from equation 2. So let's prove that statement. First, we're going to describe the sampling rate from the two groups. So R0 will be the probability of Z equal to 1 given Y equal to 0, meaning this is a sampling rate among the 0 group. and R1 is the sampling rate among group 1. In the usual IID sampling, when we collect our samples, meaning Z is equal to 1 or 0, and the distribution of Z has nothing to do with outcome Y. So R0 and R1 should be the same. But in the retrospective sampling scheme, they are different. For example, consider a rare cancer disease. Then we would expect the cancer patients would form a very small population of smaller population size. So apparently cancer patients are more likely to be sampled. So R1 is bigger than R0. Now let's look at the probability we learned when we analyze the retrospective sampling, which is this. Now, just by the definition of conditional probability is equal to the numerator divided by the denominator. Now for the numerator, we can factorize this way. So this is the probability of y equal to 1 given x. And this is basically the probability of z given y and x. And for the denominator, we can decompose as a sum of 2, and each of them can be factorized similarly as the numerator. Now let's look at how we compute the numerator. And for this term, this is basically the probability we want to learn, as we mentioned before, and it is equal to this equation 2. Now let's just take the numerator part, because you're going to find out the denominator will appear in each of the 3 terms, so it actually gets cancelled. So for this one, we get this term. Now for the first term, it's basically the sampling rate among group 1, so it's R1. So you can find out, and this is equal to this. And then we further divided R1 on the numerator and denominator, so we get this expression. In particular, we absorb R1 divided by R0 into the exponential component. So now we have a different intercept and alpha star. So you're going to find out, although the data are sampled retrospectively, when we analyze this data with a logistic model, and then the coefficients we got, and they are different from the coefficients we really want to learn, but the difference is small in the sense that the non-intercept coefficients beta are all the same. Only difference is the intercept and alpha, but that can be easily corrected. Meaning, if we take the intercept from a logistic model based on the retrospective samples, we can just take the intercept and minus this term. And this term actually can be estimated. It's R1 and R0. It actually is related to the population percentage of y equal to 0 versus y equal to 1. Meaning, if we know what is the percentage of this cancer in the general population, we can estimate R0 and R1 and know its ratio, so we can adjust the intercept to get the original alpha, which we wanted to use on the general population.